Hi folks, my name is DC Rockwell, and this is my co-host Elio Grieco. Welcome to Code and Chaos, pseudo-random tech talks about cyber attacks, gear, code, and more. And today we're probably going to be talking about gear, or rather software, that does not work properly. Thanks a lot, NVIDIA Broadcast, for messing up our first try at recording this episode. The music was coming through all distorted and syncopated. I love that word. Elio, you were the first person that got me to use that word in normal conversation. But yeah, it's awesome that NVIDIA's RTX voice worked fantastic for removing background noise. I mean, it was like magic. We could bang on a drum right next to the microphone and it would only pick up my voice. I ran a vacuum or an electric air compressor right next to the microphone, and it was only picking up my voice. So very cool application of machine learning.
Yeah.
But then they updated it into a commercial product called NVIDIA Broadcast, and now it fails. It fails, and it doesn't tell us why it failed. Elio, why is that dangerous?
Well, we're starting to use machine learning to do all kinds of stuff, like, noise reduction, generating images, driving cars, which is where it starts to matter a lot more. And that's a fun thing that a lot of people don't realize. There's, as cool as machine learning is, and I hate the term AI, you'll find a lot of people in the field will not use the term AI because AI, of course, is artificial intelligence. And it's definitely artificial. It's man-made. But none of the stuff, I don't care which one you want to quote, GPT-3, IBM Watson, anything newer, none of these things are intelligent for any reasonable definition of intelligent. None of them. Now, machine learning, that term is accurate. It's different than regular coding because you don't just write the code and you tell it exactly what to do. You kind of write code that could do something useful and starts out just useless, like a random number generator. It does nothing useful. And then it has to learn. You shovel data into it. And as you shovel in more and more data, it gets smarter and it starts to find patterns and it starts to react according to those patterns. And you can teach it to do some pretty cool stuff. But that's the interesting thing is because you're teaching it, it's kind of a logistic curve where it'll start really slow and get a little bit better very slowly. And then in the middle of the curve, so really slow at the beginning, a lot of the traditional like convolutional neural nets and the deep convolutional neural nets, which were super popular and are still pretty popular, but there's some better approaches now that are more interesting that are starting to dominate the cutting edge discussions. They would need like thousands of examples is still the beginning of the curve. And so they would barely be getting better. And then once you start getting into hundreds of thousands of examples, they start getting reasonably decent-ish, still pretty bad. And then as you start getting into millions of examples, they start getting pretty good. And they start rapidly increasing as you keep upping the number of millions. And then as they get into tens, hundreds of millions of examples, they start getting pretty impressive. And that's where people start they publish papers and you see these crazy headlines like, oh, it invented a new language. And we'll come back to that, all that kind of BS. But it really looks cool and it does some neat tricks. But the problem is it doesn't just slow down as you start putting in billions of examples. It doesn't just not get better any faster. It does that, but it actually, there's a thing called catastrophic interference or catastrophic forgetting where it'll be really, really, really good at doing like, let's say image classification and you show it an image of a cat and it's like, oh, that's a cat. And I'm like 98% that is a cat, 98% certainty. Well, as you dump in more images, suddenly it'll just forget. And you'll give it the same picture that it was 98% certain about. And it'll be like, a dog, a cat, a bird, I don't know. It's like 40% certain that is. And we don't know how to predict this. We don't know when it will stop working. So I don't know. We haven't had any time to debug this. We were supposed to go on at 5:30 Mountain Standard. And I was like, whoa, before we started. I'm like, DC, that music sounds awful. I don't know if that's just the feed coming back to me, which it doesn't matter. Like I can ignore it. You sound fine on my feed, but it sounds awful. And I wish I had something set up where I could have gotten a recording, but we're like, no, we don't want to spend time troubleshooting this. Let's just get on the air. We'll try to figure it out later and get some recordings of how bad it sounds. But it could be a glitch that some programmer made an error at NVIDIA, or it could be that they threw in more training data. And the way it was manipulating the signals, it just forgot how to do that properly. And I don't know if they'll be able to reverse it. They might have to retrain an entire model and start over again. It'll be interesting to see.
Well, my understanding of how this particular machine learning algorithm works is that it's listening to my own mic and using my own mic as samples because it's coming in at a rate of 48,000 per second. And so it's taking each one of these samples and using those. And it's the reason why I could start snapping, and the first snap, you would sort of hear it. But then the rest of them wouldn't.
I forget the term. I think it's source separation. This has like been kind of a goal for a long time. One of the approaches that hopefully you could do with machine learning. There's a mathematical thing you see all over in computer science from signal processing called the Fourier Transform. And there's the fast Fourier Transform, which is an optimized version that instead of taking a long time to run, can run on modern hardware basically instantaneously. And there's a really cool thing. I'm not going to go into the whole thing, but there's a website called betterexplained.com. Actually, if you want to pull that up in the background, I don't know if they have any illustrations, but they have Better Explained is a guy, I forget his name right now, one of my favorite educational sites for mathematics, because it really is better explained. When I was teaching actually at the Grand Canyon, I did a just like 3 weeks helping out a friend who's a math teacher up there. And I was showing the kids this site. Yep, that's the one. See if you can find the Fourier Transform one, even though I'm going to talk about the sine stuff, not sine, trigonometry, excuse me. But there's a graph, even though I enjoyed trigonometry, and yeah, there it is. So we'll get to that in a second. Even though I enjoyed math, geometry, trigonometry, etc., it never really totally sunk in. Like the difference between sine and cosine and arctangent and all these other cosecant and these more, obscure trigonometric functions. He has a graphic that's just incredible on here, that it shows two graphics. One shows all of one variant, and one shows all the other variants. And it just makes it clear. Like when you're trying to figure out which one of these do I need, you're like, oh, I need that one. I need cosecant. Nice, done. And I'm like, that would have saved me. If I had seen this, if this site had existed in high school and I had seen that graphic, I'm sure I would be 10 times better at trigonometry than I am right now. So there's some great stuff on here.
Yeah, no, these are the kinds of visualizations that I see in high quality math YouTube videos, and I was wondering like what kind of software they actually use. Like Numberphile uses a lot of this stuff. What's the other one? 3 Blue 1 Brown or 3?
Yeah, that's a great channel.
Yeah, they also use these kinds of visualizations. And for those of you who are listening at home, we're at betterexplained.com, and then you can click on articles and then the Fourier Transform. And the Fourier Transform is a type of algorithm that allows you to split out, at least in audio, it allows you to split out the whole spectrum into, so if you're getting an audio signal in, you can split it out into the bass frequencies, the mid frequencies, the high frequencies, and you can you can split it out in the same way that you would see on your stereos VU meters or your EQ meters rather. Yeah. And so I'm just want to explain like what we're seeing here on the page are these animated examples that are interactive to show what's going on inside of this algorithm. So as you're watching these animations play out, you can see why these numbers end up working to do the thing that you want them to do.
Yeah, it's really cool. So the fancy way to say it, and then I'll do the really basic way to say it, is the Fourier Transform allows you to switch between frequency and time domain. So if you have a signal coming in that's varying over time, it allows you to flip that into a signal that is the component frequencies. And then if you want to do bass boost, you can just multiply the bass frequencies by a bit, or you can drop them down. It allows you to, let me switch to the simple example that I think is brilliant on this site. He's like, imagine if you had a smoothie, if you wanted to make a smoothie, let's say you want a mango, banana, pineapple smoothie, and you put those in. You put in one banana, and you put in like half a mango, and you put in half a pineapple. What if you're like, oh, this is pretty good, but it needs less pineapple and a little bit more mango? If you had a magical unblender, that's the Fourier Transform, where you could pour the finished smoothie in, and it would give you back the whole fruit that you put in before it got blended, and then you're like, okay, cool, and you take out a little bit of the pineapple, and then you add in more of the mango, and then you put it back in the blender. So that's exactly what with signal processing a Fourier transform lets you do. It lets you, if those fruits are frequencies, it lets you find all the frequencies and manipulate them, and then you can recombine them into the original signal again, which is super powerful, obviously in sound, but you can actually visualize an image as a stream of bits, and you can do similar kind of cool stuff with images.
That is the most intuitive way I've ever heard the
Right?
Fourier transform
Right.
explained.
I
I'm
love
going to
this
use
site.
that whenever anybody asks about this. And then, of course, the fast Fourier transform, or FFT, which is commonly used, is just a quicker version of that, or is there something special that's going on there?
I'm not an expert. I don't have a background in signal processing, but from what I understand, yeah, it's just on a computer, it is a mathematical, or it's a programmatic optimization to make what a Fourier transform does really quick. Because doing the original Fourier transform is pretty computationally intensive. And I unfortunately, this is our Code and Chaos. We don't do pre-research. So I didn't have time to look up what is the shortcut in an FFT versus a standard Fourier transform. But yeah, it lets you do it, like I said, on a modern, not even modern hardware and stuff going back 10, 20 years. It lets you do stuff just about instantaneously rather than having it churn for a few seconds to finish the FFT. So,
right. Well, I guess the main point here, though, is that, graphics like these can explain what's going on inside of a complex algorithm like Fourier transform. However, things like this NVIDIA broadcast algorithm, or whatever is going on behind the scenes there, and also what's going on behind the scenes of image recognition algorithms that have hundreds of millions of samples that are all being used together.
yeah.
We can't explain what's going on. How is it that we were asking for a dog, but we ended up getting a bagel? And if we could figure that out, maybe it would help us. Maybe it would help us make better decisions for our image recognition algorithms, right?
Yeah. So before we leave this, let's finish off this topic quickly. Scroll. There's a thing showing all the little waveforms and how they combine. I forget where on the page that was. But the gist of this, and there's another video we should pull up sometime that shows a mechanical integrator where basically what you're doing when you're separating frequencies is you're separating out all these sine waves. Like real sound, like music, has this really weird jaggy sine wave that looks really irregular, and it looks like it would be a beast to model mathematically. And so it turns out you can just use different sine waves at different frequencies to get these crazy, like, actual sounds. And you can deconstruct one. You can go backwards and take a really jaggy looking function, which is like normal, real audio from the real world, and you could split it apart into just a set of sine waves that are really simple mathematically to represent, and then either recreate it or modify it or whatever you want to do. Now, there's another technique, because Fourier transforms work just on sine waves. There's another technique, though, called a wavelet transform, which is really interesting and was really popular 20, 30 years ago. And instead of using just a Fourier transform, you use like example wave functions that have very different looks to them. So sine waves always have that nice smooth oscillation, but wavelets, you can have potentially hundreds of different little wavelets, and it's a lot more complicated to break something apart into wavelets. But like image compression, incredible image compression using wavelets, and not just compression. The other really interesting thing, so a Fourier transform, you can tell if there's a certain frequency of sine wave, and that's cool in music. That's how you make the graphic equalizer, right? You make the little LEDs go up for like 250 hertz for like kind of lowish bass, but not all the way low. And you just, each one, you kind of group everything in, say these are the highs, mids, lows, and you just like make the LEDs go up based on how big the signal is, which is useful-ish for music, but it's too simple. And so wavelet transforms, different images that use different wavelets, like the fact that they use certain wavelets actually lets you find similar images really, really well. So again, you can think of an image, and old TVs used to do this. They used to start at the top and swipe across with an electron beam, and they would find all of these little, they would just draw in the picture line at a time. And so a lot of the computer stuff is the same way. The picture you're seeing on screen, you can unroll a line at a time, and you can represent it as one really long line, where you just snip it and then you move the next one down under it, and that's how you get a square. And so really you can think of an image as a signal and do some cool stuff with it. So wavelets, not just for incredible compression, they're also useful for, like I said, analysis. And is this image similar to this image? What if I scaled it up or scaled it down or made it black and white? Well, it's still the same image, so it's still going to have some similarities aren't going to disappear even as you modify it. So really cool technology.
Yeah, I mean, and there's not many, the stakes aren't really high for these kinds of applications to not be explainable. But aren't they having the same sort of problem with self-driving cars and other kind? And is self-driving? Well, I would imagine self-driving cars right now are probably the most dangerous, right? Or are there other places where they're very dangerous?
Yeah, let's get into that. So the Holy Grail. So again, we've talked about Fourier Transform and wavelets, but still they have limitations. Even wavelets are very cool, but there's still limits. So the Holy Grail is, what if you could find any pattern instead of just sine waves, instead of more complicated a set of wavelets that you're building? What if it could literally potentially be any pattern that's there? And that's what some of these like convolutional neural nets and deep neural nets, which are just same thing but much bigger, many more levels of neurons tied together, they're really good at that. And that's what the thing that we're complaining about, NVIDIA, tried to build this really cool system that does what's called source separation. And instead of classifying by frequency, which is fine, like, some instruments have a relatively narrow range, like a drum tends to have, a certain sound for a certain drum, and it spikes at a certain, and then it kind of drops off. So you could probably identify drums, but someone singing, there's a wide range of frequencies that any number of humans, you have sopranos, you have tenors, you have all over the spectrum. And so what if you could just say, look, I just want a human voice. Find the part of the signal that is a human voice. Find the part of a signal that is a trumpet. Find the part of a signal that's a snare drum. And actually, that's what NVIDIA was doing pretty well until like a day or two ago. And there's other research too, but it's really cool because now, even if someone didn't record in a professional setting and they didn't record audio with like 16 tracks where every instrument, every vocalist is separate, we now have the technology. We have like a super ultra steroidal, like Fourier transform on lots of steroids, and just, we can pull all the pieces apart by what they are, the way humans think of what the different pieces are, rather than just by frequency, which is absolutely incredible.
Yeah, it was magic the first time that I used it. It was amazing. And you can get examples of this on YouTube, by the way. If you go on YouTube and you search up RTX voice and you pull up pretty much any of the high view, videos that are on there, it's incredible. It's truly a magnificent application of machine learning. It runs off of an NVIDIA graphics card, so it doesn't even tax your CPU. It's very fast. I think we had 200 milliseconds of latency for the entire thing to happen, which, that's not terrible. And we could adjust the video and everything for that very easily. Actually, I think it was 100 milliseconds.
That's pretty impressive.
In the end. Yeah. It was very, very, very low latency. But it stopped working, and now we don't know why it's not working. We've gone to the NVIDIA forums, and the NVIDIA forums are just full of lots of people saying, trying to explain the phenomenon that they're hearing. They're like, so it's kind of garbled with some clicks and some crunchies, and, how do I spell, like...
A lot of Ks.
Yeah, a lot of Ks. So
still easier to spell than Hanukkah.
It's very difficult to ask for help when it comes to these kinds of algorithms I'm finding, because you can see dozens of people struggling to do this on the NVIDIA forum right now. Yeah. I decided just not to do it. I decided, well, you know what? I'm going to deal with some background noise for a while until they iron this out. I'm sure they're going to figure out a solid, a solid algorithm that'll work with this, a solid data set or whatever they have to do. But until then, it's alpha or it's beta software. And last time we used beta software on this thing, you know, we got frustrated and quit. So we're not doing it this time.
Well, and that's the sad thing is ever since the internet really got popular, there used to be a strong distinction between alpha level, which means there's concept, someone has an idea. Alpha means they've started working on the idea, but there's a lot of features missing. Beta phase means, okay, most of the features are in there, but we haven't tested it very much. They're still buggy. It still might not work properly. And then you get to final candidate, which means, okay, you might have several rounds where we think we found all the major issues. We think it's good. And then eventually we used to get to final release where it's like, this is the released version. Because we used to have to put software onto actual disks and stick them in the mail and pay, like a company like Adobe that's sending out like 50 million Photoshop disks. That's expensive. Buying all the disks, shipping all the disks. You screw that up, you got to send out a second set of disks. That's a lot of money to waste. But now it's the internet. So we just send software that we think is kind of sort of okay, you know, whatever. And you can just download an update, you know, again and again and again and again. And we don't even worry about fixing all the bugs in the second or third update because you just always download another update. So
yeah, I don't know. Your definition, you sound like the definitions of alpha beta software are just universally understood, and they are not. Every place I go, they redefine this as whatever the heck they want it to mean.
Probably part of the problem.
I personally define alpha software as anything you're doing internal testing on. You have not released this out to people who aren't working on the project. Once you have people who aren't working on the project, who aren't actually, you know, contributing to the project using it, you're already in beta. That's what beta means to me, is that somebody on the outside is now depending on my software to work. And I can't just say, well, fix it yourself. And then we have release candidates after that, which are like, well, I think I got it this time. What do you think? And almost never do you actually have it right on the release candidate 1. Then you go release candidate 2, release candidate 3, until you have something that's fairly solid, something that you feel is truly actually going to work. And then you release your 1.0. And I follow semantic versioning, which you can go to Semver.
Well, you should.
Right. You can go to semver.org if you want to learn more about the semantic versioning specification, but it essentially says that the major version, like 1.0.0, so there's 3 numbers in it. The first number is your major version, your second number is your minor version, your third is your patch number, and the first number changes anytime that you break something in it or change something in it that, well, not break it, but if you change, it's called a breaking change. But really all it means is you've changed something that if someone else is building a technology that integrates with this thing, and you've changed something about this, so that way whatever they built will break if they upgrade, then you have to change it. And that means if day 2, the second day, you know, you released it, and then the very next day, you've changed a feature, so that way somebody else out there's system might fail if they do an upgrade, you're already on 2.0. That's how Semver works. You can definitely get up into like version 143. You know, that's completely plausible. And in fact, a lot of software does do that. But then I find that in the corporate world, there's this big aversion to having big version numbers. People want everything to sound like, you know, the software that you've seen in the past, you know, like 90s software versioning, where it's like we're on Windows 3, and then you know, like at least we're not at the end of the century, so we don't have to name everything after the year, you know, like Windows 95.
that was dirty. So there are some people that break Semver. There's actually quite a few companies, unfortunately, that break Semver. And that's really evil. It really makes the version number basically useless. And one of the ways they broke it, Microsoft early on, I think, were the ones that started naming it by the year. And the reason they started doing that has nothing to do with software engineering. It has to do with the sales department. It's the same reason cars have a model number that's based on the year rather than a version, because that way, if it's, you know, 2021 and you have a 2020, oh, you don't have a new car. It's time to go buy a new car.
Well, I was just going to say that works. That can work, but it only works if you are truly only releasing something every year. every single year with nothing in
Yeah.
between. And like, for example, I've seen software which is versioned like 2020.12.13. And you're like, okay, that came out on the 13th of December, 2020. That makes sense, except when somebody wants to do 2 releases in the same day. Now we need hours. Oh wait, but hold on. We have a hot fix that had to go out 20 minutes later. Okay, now we have minutes on there. Oh wait, we have an automated build system that now goes off of every commit. Now you need seconds on there.
Yeah.
And sometimes, just sometimes, 2 commits come in on the same second, and it's just like, oh, well, hold on. Now we need milliseconds onto the thing, and you have this
A and a B.
huge. Yeah, but at the end, you end up just with a timestamp. An epoch works better than that, but an epoch is the number of seconds since January 1st, 1970. But it's just like SemVer, the reason why that standard exists is because we can, as humans, look at this number and quickly learn a lot about it. We can learn a lot about, like, if we were on version 1 and we're suddenly on version 2, we know that some big breaking change came through. Something that we're going to have to change our software. If it integrates, we're going to have to change it. If something has a minor version increased, it means that there's a new feature and that we may have to add something to our software to take advantage of that feature, but that none of our other features are going to be broken. And the patch number just has to do with, we didn't add a feature, but we've enhanced a feature, and there's nothing you have to do. It's safe to update this if you're doing it right.
Frequently, it means we fixed a bug, because there's always bugs. And so, and I've heard that. So you call it patch. I've heard that also called micro, major, minor, micro. So
the actual SemVer, I think, patch? Let me double check. But yeah, I'll pull it up here on the big screen here.
Just so people are.
Yeah, major, minor, and patch.
Oh, interesting. Okay. I thought it was micro, but interesting. Okay, cool. So the problem, though, with doing what you're talking about, besides it gets really long and all that, and you might have colliding versions, is there's no meaning. It's non-semantic when you just timestamp your code release. And so I have no idea, like you're saying, if I see that you've gone from version 2 to version 3, I can say, oh, okay, well, we need to actually get the team together. We're not pushing this out on a Friday. We need to start planning and talking about what did they add, what broke, how are we going to accommodate that change in our system. And so it gives us as developers really helpful information. And it goes even into like the Ruby on Rails. So Ruby Gem and Bundler have, so those are dependency managers. So when I pull in other people's software, so I don't have to write the whole thing from scratch, I can actually tell it, I have equals, I have greater than, I have less than, and I have this cool operator called, like, I think it's tilde arrow, the squiggly arrow operator that says, depending on how far I specify down. So if I say version 2 with tilde arrow, the squiggly arrow, it will automatically, anything 2.1, 2.2, 2.3, 2.30, whatever that second minor number is, it will go ahead and upgrade automatically. If I do 2.2.0, then it will only upgrade stuff where the patch number changes, but it won't go to 2.3. And so some of the tooling in JavaScript, in Ruby, in a number of languages actually uses SemVer to make sure that the build system doesn't accidentally break anything by upgrading to an incompatible version. But if you just name it whatever the heck you want, that doesn't work anymore. You don't get to use that tooling. So it is actually pretty important to do SemVer.
I'm not sure. I'm looking it up right now, but I believe, let's see, the squiggly arrow. There's cool names for these, by the way, the actual operators. There's the optimistic operator. There's the pessimistic operator. And then I believe, it doesn't give me a real name for the squiggly arrow.
I can't remember if it has a special name.
But I believe that what that does is it gets all of the patch numbers only, and it doesn't update you for minor versions. So it's as I remember the spec, it depends on what you define. If you define a minor version, it only upgrades patches. If you define only a major version, then it will upgrade minor versions as well. So it's basically shorthand for optimistic or pessimistic. Yeah, but I love how it's optimistic and pessimistic as a naming convention because that's basically what you have to do these days is be like, well, I'm kind of optimistic that if we set it like this, it's not going to break everything on the next gem or bundle update.
Yeah.
So
So
NPM also uses this
Yeah.
for, and I would imagine just about every package manager out there for today. Well, I would imagine like Python and
I don't know about that. Python has a horrifically bad their patch or their dependency management. They have pip, they have pipx, they have venv, they have like a dozen things that all do slightly different stuff. That in like Rust in the cargo package manager with crates, in Ruby with gem, in NPM, like everything's integrated in one place and there's just one blessed package manager. Python has still not unified those. They have a whole bunch of different things that kind of sort of interoperate. There's an XKCD about this that kind of actually diagrams out all the insanity. But that's one thing where Python's getting really popular. And somehow, even though Python is a few years older than Java, they still have not figured out package management. It's like, come on, guys. One of the best things about Python is all the cool little libraries you can pull in and utilize. And it has some of the worst package management out there right now in any modern programming language. It's fix your stuff, Python guys. Get on it, Guido.
When I type in Python package manager into Google, it auto completes to Python package manager like NPM. those poor devs, you know.
It's just insane. It's like worst tooling out there, just awful tooling.
Yeah, I mean, there's some real great software written on Python. I guess, there's real great software written on basically anything that's Turing complete, but it's that Python has a huge volume of good software. It's just that package manager that really turns me off to wanting to work in that space or really seriously dive into Python. It's cool though. I mean, it's a neat. It's neat. I don't want to talk too much smack on. Well, I don't want to talk too much smack on Python's like tabbing convention because the truth is I don't even really understand why they do that. For example,
I don't think they do either anymore. Go on.
Well, the readability of any Python file I've noticed, like the tabbing makes it very easy if you have small, well-defined modules. I can clearly see what's going on with the tabbing, and I have no problem with small files. But once you get into larger files, which, let's face it, most coders take advantage of as many lines as they care to in a file. Once you have those multiple nested levels where I lose track of which level we're on, and I have to start using an IDE that will create lines in between them, and then there's so many lines that I have to install a second plugin that will color code those lines, and I have to do all this stuff to make it so this way it's readable again. And for me, that really detracts from the usefulness of the tabbing for me. But I do like that it's Ruby-esque, and I like how I don't know this for sure, but I heard Python's very performant.
No, that's not true. Both Ruby, Python, and Perl. No, they're all interpreted languages.
Well, then why would they use it for data? I thought big data and science, uses Python a lot.
I'll explain that. It's very big in cybersecurity and data analysis. But so the thing about, and sometime, I don't know if I want to spend the rest of this show on this, but we should talk about it sometime. And I actually have notes written up because someone asked this on LinkedIn. So I gave them a really lengthy response. When you're going to choose a language for a project, there's a number of criteria of like, what language do you choose? And some of those, I think there's about a dozen. I don't have the notes up right now. And again, I don't want to waste time on this show, but briefly, one of those is language theoretic, like the language itself. There are different ways. There are imperative languages, declarative languages, logical programming languages. There are functional, concatenative functional. There's all kinds of, there's probabilistic models for modeling populations and traffic flow. Like there's major categories of languages that when people say, once you learn one language, you could just program any language. That's a bunch of BS. Once you learn one imperative procedural or imperative OO language, which is the popular kind, which is Java, JavaScript, Python, Ruby, a whole bunch of others. Rust kind of falls into there too. Once you learn that, you can pretty easily, it's mostly syntactic differences and little minor things that are pretty easy to adjust to if you switch between that category. But if you jump from that to something like Haskell that's functional, or something like Prolog that's logical, it's going to hurt. It's probably going to take you longer to switch than it would take if you just started fresh in Prolog or Haskell. And Dijkstra had some, E.W. Dijkstra, a huge name in computer science, actually had some writings about why you should start in Haskell and then move down to something like JavaScript or Java. But again, separate episode about education and getting computer science. So that's one thing. Most languages, that is not high priority. It's not, I would choose a language. It should be, but it's not. So the other things are the community. And Python does have a phenomenal community. There are tons, like hundreds of thousands, if not millions of people that are really helpful. And if you're like, how do I do this? I'm trying to learn this. Where do I go? Tons of stuff written, tons of videos, tons of interactive stuff, tons of message boards and Slack channels and IRC and everything else, and meetups where you can go and be like, guys, I don't know how to do this. How do I do this? And they'll help you. So that's a big thing. And businesses want to hire a lot of people. So you want a language that has a lot of popularity, even if the language theoretic aspect, maybe it's not great. But it's like, whatever, we'll buy 20 more servers, but we want to be able to hire people easily. And then the other thing, which is what you were asking, okay, they're doing all this machine learning. Python must be fast. Not exactly. There's something called an FFI, or a foreign function interface, that allows you to glue different stuff written in different languages together. And I don't know if this technically fits under FFI, but both Ruby, Python, I can't remember if Perl, I think so too. Perl's the granddaddy, used to be the biggest thing on the internet, the duct tape of the internet. And Perl, Python, and Ruby are all very similar languages. They're more similar than not. So I won't say they're interchangeable, but they're very similar. So if you need performance, because these are interpreted languages, because the machine goes through and turns it from human readable code into something the machine can use while you're running it every time you run it, that's one reason they're all slow. The other reason is Ruby, and I think to a lesser extent Python, Ruby allows you to override anything. You can override objects, like open up an entire class and make changes, and it's very powerful and fluid. In Python, similarly, not quite as much. You can't like add strong typing by just messing with the language, like contracts.ruby, and I forget the other one before sorbet. You could like add in a dependent typing system into Ruby. It's so insanely like extensible. So it's slow. And because of that, you can never highly optimize a loop. If you're doing a loop, every time you're going through this loop and adding a number, you have to stop. And before you call, first of all, the number could get overwritten. Not a good idea, but it is possible in something like Ruby to like override a number and turn it into something else, which is a terrible idea, but it is possible. And then all the functions you're calling, the methods rather, they might get overridden. So you don't just go into the loop and do the operation and then check the condition, do the operation, check the condition. That's C. And so blazing fast inner loops. In Ruby, you go into the thing, you have to check, did this get overwritten? Did this get overwritten? Are these all the same? Do the operation, check the condition, go back in. There's a lot more steps you cannot get rid of because the language, the way it's specified, and Python is somewhat similar. There is some work on JIT stuff, just-in-time compilation, that helps with that. So Ruby's gotten faster. I don't know if Python has a JIT yet, but again, you're still limited, still way slower than Rust or C. So a lot of these things that they're calling are actually written in C and starting to be written in Rust. So the stuff you're calling, when you're calling NumPy, SciPy, all these amazing libraries, what's the NLP one? NLTK, none of that's written in Python. That's highly optimized C code that then Python uses an FFI to then, and Python does have one cool trick where if you're not modifying the memory that comes back from the C module, then it's really efficient at taking that memory and not copying it, which saves a ton of time if it's a big chunk of memory, and allowing you to just keep that memory and not leak the memory and operate. And Ruby doesn't do that. That is one cool language kind of, I won't say language theoretic, but it's one language feature that is why Python specifically versus Perl and Ruby has become really popular, is that ability in a lot of cases when you call out to some model, you say, do some cool, super awesome computer science in C, and then it's like, all right, I'm done. Here's your result. And you can just take that memory and just take ownership of it and then do whatever you need to and then throw it away without having to first copy it over into another variable that Ruby owns and then do stuff with it. So Python's a little faster in that regard.
So I'm not sure if that's true. I mean, gems have native extensions, which are
Oh, yeah.
wrappers around C. I thought it's the same thing. Is it not?
Oh, no, that's very similar. It's that ability, the one thing, because I was like, why Python? Why not Ruby? Because Ruby can call out to Rust and C and all kinds of stuff. It has an FFI. But it's that ability to hand the memory back and not do a copy. Ruby wants it copied into a variable that it can own. And the FFI, it's like, hey, whatever FFI stuff, that's your memory. You deal with it. You clean up after yourself. Not my problem. So it wants a clean copy back into the Ruby memory space, whereas Python is like, no, I'll just take that. Don't worry about it. You just leave that memory to me. I will deallocate that properly later. So one's minor advantage, but yeah, anyway, that's what's ironic is Python is basically a really clean looking glue for all this C code that lets you do these incredible things, but none of it's Python. It's not fast enough.
Right.
So,
but I mean, to me, that's fine. You know, like I mean, in terms of where we're at right now with code, you know, like for example, you probably wouldn't want your no offense, junior engineers out there, but you probably wouldn't want the junior engineer in charge of the highly optimized loop in some sort of a thing. You are probably going to want somebody who really, really understands the memory allocation, understands the computer science of what they're doing.
Yeah, totally.
You would want them in charge of the C, but you also don't want that same person who's doing that highly optimized loop to necessarily be, you know, arsed with having to do a bunch of, you know, basic business logic higher up, right? And so for me, these kinds of languages are great for companies and for you know, for startups, because you can have a senior engineer or even you know a computer scientist in charge of this C library that's doing these highly optimized special sauces for your company, and then you can have you know, just, you know, you can have all different other kinds of engineers in charge of the business logic. And to me, that's the best of both worlds, because, you know, you wouldn't want to necessarily write your web app in C. You know, you would you
knew that would be a terrible idea. You definitely would not want to do that.
Right. And I mean, like, even Objective-C was pushing it, you know, like that was like, you know, like, I kind of hate this, you know? And so, you know, I think it's a great compromise between these two worlds, which, you know, let's be real, the disciplines involved in doing these loops and the discipline involved in doing highly optimized code and business logic code, your concerns, your training, the RSS feeds you subscribe to are different. You know what I mean?
Yeah. And that's where Rust is really exciting, because it gets really hard when you're really tightly optimizing code. And I'm not an expert in code optimization, but I've done a little bit. But one of the biggest problems, just like the machine learning stuff that I want to get back to before we finish out here, is there are optimizations that they'll collide, and the one optimization will fight with the other. In fact, there was just a regression in, which language was that? Python? Was it Python or JavaScript? Anyway, there was just a thing the other day I came across this optimization. No, it was JavaScript, because it was in this one code challenge or something. I can't remember if it was an advent of code or what it was, but there was a pathological edge case where when you ran it in Chrome, it took forever. And the reason that one of the engineers, he got tagged, and he's like, oh, I see what's going on. I filed a bug. We'll fix it. But there's two different ways. If you do like a hash table, there's two different ways in JavaScript. There's a fast and a slow way of indexing into there. And so there's a heuristic code. So not quite AI, but heuristic is like super lightweight AI. It tries to make some decisions based on incomplete knowledge. And what happened was they found an edge case. They just happened to hit this case where it kept switching back and forth. Like every way through the loop, it would switch, which would mean it had to copy everything over from the fast hash lookup to the slow hash lookup to the fast hash lookup to the slow hash lookup. And it was thrashing between these two lookup types. And the heuristics were just like, it couldn't figure it out. So it was just bouncing back and forth. And it made it really, really, like, we're talking tests at sub-second completion on Safari and Firefox. In V8 and Chrome, it's taking like 10 seconds to complete this test because it's thrashing. So there's weird little stuff like that where when you optimize this little heuristic optimization to make sure it's as fast as possible, actually in this one case that no one else had run into yet, makes it like dreadfully, painfully slow. And so, yeah, optimization's hard. You have to not just understand the code and how it's running, you have to understand the levels above and below it and how it's going to interact with both of those and be able to try to anticipate. And then if you find one of these bizarre edge cases, then track down, all right, what happened here? This was supposed to be way faster. It's way slower, like thousands of times slower. What the heck happened here? So yeah, that's for senior devs. Like that's something definitely to aspire to, but tightly optimizing code is super hard, and it's also dependent on platform and stack and everything else. So
yeah, this is why I hate whiteboard interviews, like because they're essentially hiring for those folks. They're like, and you when they well, I mean, I'm not saying they're hiring for that. That's the kind of interview you would use to hire for somebody who's going to make highly optimized loops, who's going to invent algorithms, somebody who is going to be an expert in carefully choosing the right algorithm without needing Google, and whenever I walk into these interviews, my first question is, where in my daily responsibilities am I going to have to figure out this kind of an algorithm?
Balance a binary tree like that. Right. The data structure has that built in. I'm not going to engineer that unless you're hiring me to design data structures. No. Why are you asking me this?
Yeah, this is why where I work now, I'm so happy they let me do a take-home project. They gave me a list of third-party APIs and told me to build something cool with those APIs. Nice. That was it. And I came back. I built this cool thing which helps animals get adopted, and it was awesome. I liked the project. I wanted to keep going with the project. But it was more than that. When I got into the interview, we were just talking about, hey, why'd you choose this? What was your decision-making process in coming up with this optimization? And it was a great conversation because I was talking to people about a project. We weren't having to do the coding in front of each other because, that's how often do you end up doing your code in front of other people? And if you do, you're usually pairing with them and working together, not actually one person just sitting there working with another person looking over their shoulder the whole time. That's not very.
That's Rust programming. That's what Rust programming feels. The borrow checker's like, see that? You screwed that up. Try again. Which is actually awesome once you get used to. Oh yeah, Rust programming is like doing high-level C++ programming and having a senior dev just stare over your shoulder and point out everything you screwed up, which is super frustrating at first, but then once you get used to it, is super helpful. Like I'm not going to go into the whole thing, but I tried to pull in a non-reentrant library to do some fancy crap in a threaded scenario, and it didn't have the sync trait, and Rust is like, no, that's going to blow up in a weird way in production. I'm not going to compile that. Like, you're asking for trouble. No, try again. And I'm like, oh yeah. I forgot about that's not reentrant, so that shouldn't be used there. Thank you, Rust. Like, I wish it would compile, but I'd rather have Rust yell at me and tell me I did something stupid up front and be able to fix it before there's ever a problem than ship it into production and like, oh, what is going on? Why can't we recreate this bug, right? So yeah, Rust is very much that experience, but I think in a good way. I like that personally, so...
First off, Rust sounds awesome, and I do need to look into it more. But we only have a couple of minutes left. We have like 10 minutes left, and there was one thing I really wanted to talk to you about today, which was there was I guess the news published today that the first sustained long-distance quantum teleportation was achieved.
Oh man, we should save this for another show. But this is big news if it's... I haven't had a chance to dig into that, but yes, that's big news if it's true. Okay,
so it's using the principles of entanglement, and yeah, I think you and I can dive into this later, but the news today was that they were able to successfully transmit a sustained signal,
Maintain
of
an entanglement
qubits
over a distance, yeah.
of 44 kilometers or 27.3 miles with a fidelity of 90%. And that's good enough for you can do handshakes and, you can get over that. That's no problem, Yeah. 90% is pretty good, actually.
That's really good. Yeah.
And my understanding is that there's almost zero latency involved with this,
There
right?
is zero latency. If from what I understand, again, I want to have James on here because he actually understands some of this. He was actually in another video thing we did on, I think it was Security Coffee House, or it might have been just a personal thing. But he was mentioning like some of the misconceptions where people are like, oh, a qubit is a 1 and a 0. And it's like, it's not. That is a oversimplification that if you don't have to build anything, you're just trying to explain it to someone kind of close enough. But it's not actually true, and that's not how it works. And if that's your understanding, you definitely won't be able to use quantum computers for anything because it's not what's happening. So like when you're talking 90%, problem with quantum computing is you have the Heisenberg uncertainty principle, where basically when you take a peek, that superposition where it's all the possibilities collapses down into some final thing. And the problem, it's not just you that can take a peek. Anything from reality that kind of causes, quote, an observation can collapse the superposition. And I'm going to have James point out all the stuff I'm saying is way off on this, but you have to fight the real world. Like all this entropy is trying to like sneak in, and we're talking physical entropy right now, not cryptographic. It's trying to sneak in and mess up your quantum computer. So instead of having one bit of atoms, like let me not use the term bit, one little grouping of atoms, and just doing the computation once, you generally have to have a whole bunch of groupings. And then a few of them are going to kind of get messed up and corrupted. And you're going to have to just take the average and use the ones that are, okay, well, most of them say this. Most of them didn't get corrupted, we don't think. So that's our final computation. The rest of them we got to throw away. They, entropy snuck in and ruined it for us.
Well, let's definitely get him on the show, and let's dive more into qubits later. But I do want to I do kind of want to nerd out for a couple of minutes on the implications of this for society.
Oh, yeah.
Because the quantum entanglement, my understanding is it was first postulated by Bell in Bell's theorem. And this is what this is the exact thing that Einstein meant by spooky action at a distance.
Indeed. Einstein hated quantum.
But it was especially entanglement.
Yeah.
And Bell's theorem predicted that an entangled is it an entangled particle or I don't know?
I believe
entangled atom. I don't know how it works.
You can use atoms, photons. It's got to be a particle, I believe. But
gotcha.
Yes, it can be a number of different types.
But it entangles these two particles, and you can take one of them and put it over any amount of distance. And when you change the spin of one, the quantum spin of one of them, the other instantaneously switches. Like, whoa, man. Like, that is some really spooky, crazy stuff right there. And the fact that we're beyond experimentation now. Now we're into application. We're into actually
early application, but yeah.
Well, yeah, early application. But I'm saying like we're able to make. They just made the first basic entanglement phone call that was sustained, and that is crazy. That means it's not theory. It's not sci-fi. It's not sci-fantasy. That's a real phenomenon. That's really demonstrable. Yeah. And so over 44 kilometers, they were able to change a bit, and 44 kilometers away, instantaneously, the other bit switched to the opposite. Like, or however it works. I thought my fuzzy recollection is that if you had a 1 on one side, you switch it to a 0, and it has to do a spin or something like that. But the point is, if you switch it, the other is going to show the exact inverse of it, and it's with zero latency. So this would
may
mean
have to give some context though. Like, why is that so cool? Because over 44 kilometers, who cares? Light's fast enough. I don't care. So why is that cool?
That's cool because you could possibly have a satellite if this holds up over greater distances, then we could have a satellite around Mars, and we would have somebody on Mars who could communicate up to this satellite, and the satellite would be able to beam that back to us. We would have real-time communication between Mars and Earth. We could have real-time communication with satellites like the Voyager probe that are on the outskirts of our solar system, where we don't even need a line of sight to the thing. We don't. It could be anywhere in the universe. We could create clusters of these and start shooting them off from Earth in every direction. And these things would instantaneously give us real-time monitoring back to Earth of what's going on with them. That opens up so many cool possibilities. But for me, it's cool in the short term because it almost seems like within 20 years or less, this is a foundation for being able to create a new internet, the way that you were talking about with strong digital identity. No, hold on. What I'm talking
20 years
about
seems optimistic. Eventually, yes. Probably not 20 years.
Well, keep in mind, we don't have to lay down new fiber. That's the whole point.
There's a lot of other harder things than laying fiber, though. When you're talking about quantum, keeping that entropy out and all this, I think 20 years is super optimistic. Someday,
maybe
totally,
so,
but 50 to 100 years.
But still, the new internet that's going to replace our current fiber infrastructure, if this holds up, it seems it's almost certainly going to be quantum in nature.
Yeah.
And it's going to. We will have no need for wires. We will have no need for cables. My monitor will be able to instantaneously communicate with my computer.
You're still going to have some cables. Unless you're doing wireless power transmission, you're still going to have some cables.
Maybe power, but I'm talking about data transmission.
But that's the thing. Right now, this stuff is stupidly expensive and difficult. And so this idea that we just replace everything with quantum
computers.
Yeah, but they didn't happen overnight. They took a half century at least to kind of get to the point where everyone could have lots of them. They're still pretty pricey when you think about it. They've come way down, but a flagship phone is still $1,000. That's not cheap yet. That's cheaper compared to what it used to be, but not cheap. So,
well, how much was the first cell phone?
Yeah, I mean, again, there's been massive increase, but it's not like anyone can just go to a vending machine and buy a $5 cell phone that's got all the smartphone amenities. That's not a thing yet. So I'm just putting it in perspective. If you have to communicate across, great distances, this is amazing. And there's another aspect that before we totally run out of time, I want to touch on, but you're not going to replace you're not going to use quantum teleportation, quantum entanglement to send signals to your monitor. That's going to be hundreds of years out before it's that cheap where you can do something like that, because you're still going to have to give it power. So you're already running the cable for power. The latency at the speed of light from 3 feet away is so insanely small. You would not use quantum. This is like the blockchain people it only uses 50,000 times more energy than we do. Let's blockchain it. And you're why?
I'll give you I'm being highly optimistic about it happening maybe in my lifetime or whatever, but I do see this as being one of those almost every technology we have, eventually becomes stupid cheap, right?
Eventually.
And I'm just saying, once it becomes that cheap,
sure,
there will be a future. If this holds up, if the trends keep going, if we don't kill ourselves before then with some horrible pandemic.
That's probably 50 to 100 years out. I agree with you, but 50 to 100 years out, not 20 years from now. This is not 2040 technology. This is 2100 technology. So
I just went from super excited to super depressed that fast.
I mean,
I want to be here. I want to see it.
The one thing before I get off of this, the one thing that we really want to mention is, so one is, yes, the latency free communication, but the other, wait a minute, how is it latency free? And this is what's really interesting in a cryptographic context. And the quantum computing is like a boogeyman, oh, quantum computing, we can't use cryptography. And it's first of all, no one has a 128-bit quantum computer. No one has a 4096-bit quantum computer. So theoretically, in an RSA is hosed, practically, probably 10 years at least till anyone actually builds a 4000-bit quantum computer. So nothing to really worry about. And we're already talking, there's already a third round NIST has already released the third round evaluation of post-quantum or PQC ciphers. So anyway, but the biggest thing is because there's no latency, and we still don't fully understand this, and we might have an advance that nullifies this aspect. But in theory, there's no there's no cable to tap into. There's no radio transmission to intercept. So not only is it instantaneous, which is cool, but in theory, if you had quantum entanglement, the information is just here and here at the same time, and there's nothing to intercept in between. So you don't even need encryption. If you can actually do this, the data is 100% secure, not just instantaneous, but you can't intercept the data unless we find a way to cause another particle, a third particle, to entangle with the other pair, which we're a long way off. We have no idea, from everything I've read, no clue how to even try it. We're barely getting two little particles to entangle, let alone like randomly like forcing an entanglement with some other arbitrary particle. So that is like, yeah, Shor's algorithm, Grover's algorithm will threaten modern cryptography, but quantum communication will totally obviate the need in a lot of cases. If all these hold up, you won't even need encryption. It just, data goes from my phone to your phone instantaneously. It's just on both of them. And we don't have to waste time encrypting it because no one else has a way of intercepting it.
Well, one can dream that we'll have a breakthrough, and I'm going to have my sweet cable. Well, let's be real. Even if they came out with it, I probably wouldn't afford changing out all my gear. So
as cool as we're geeking out, like as cool as it would be just to say it's quantum, like for normal people, there's no direct personal benefit from quantum computing. Now, the government and companies protecting your information by not having a way for people to intercept it, you'll see benefit from that. Like breaches will become much harder, maybe almost impossible, but extremely difficult. And so there will be benefits to society. But as far as you, like quantum entangling between your your computer and the monitor, like a cable's just fine, man. A cable or just RF that with a decent encryption key is just as good, and it's way cheaper, and we have it now. So why wait?
I mean, and plus, I mean, like, let's be real. I collect like vintage computer stuff anyway. As soon as quantum computers became cool, I'd start thinking cables are cooler, So whatever. I'm a computer hipster. All right. Anyway, that brings us to the end of our show, folks. And I'll let Elio get in a last word if you'd like.
I don't have too much else, but we'll have to come back next time. We tangented way off, but we'll talk about learnability, explainable AI, and those kind of implications next time.
Excellent. All right, everybody. Thank you so much for listening. We will have another episode for you tomorrow, so just stick in there. We're going to rethink our release schedule, but we'll get to that next time and when we have an announcement. So everybody, thank you very much. This was Code and Chaos. I appreciate you listening. Have a good night.